Hello everyone. So let us start today's session. This is session number 17 and today we are going to see the basics of Gauss-Seidel Power Flow and if we see in the last class we have been seen that the nonlinear problems are very difficult to solve and it usually requires an iterative approach. So that nonlinear problems and what are the major contribution for the that make our power system nonlinear? These are constant power loads and current injections. So these are the things. And now we are going to look into we have also seen the methods to calculate the bus admittance matrix. That is one of the important element in the load flow study. And in continuation of that, we will see what is the importance of bus admittance matrix. And here we can see that with the one known element, either voltage or current, we can find the other element, voltage or currents. So the first point is that if the voltages are known, then we can solve for the current injections. That is, I we can find. We have already known this by bus from the characteristics of transmission line, and we have been given with voltage. Then we can find the current injections. And the second point is that if the current injections are known, then we can solve for the voltage. That means if this I is given and by bus we can find by the given the parameters of transmission line, then y bus inverse of y bus is z bus. That is bus admittance. Sorry, here one mistake is there. Bus impedance matrix. This z bus is the bus impedance matrix. Now let us see the one example. From there we can see that how this bus admittance matrix help in finding the other value if one known quantities are given. So let us see here we are given with two bus power system. At bus 1 we are one generator is connected and the transmission line resistance and reactance is given by 0.03 plus J 0.04. So it is one load is connected at bus 2. So this is bus 1 and this is bus 2. And it is also model by the model of shunt admittance. So it is by C divided by 2, that is J 0.1. Now let us first make the equivalent electrical schematic of this bus and this two bus system. So here, so this is J 0.03 plus J 0.04 and J 0.1. So this is the current injection at bus 1 V1 and bus voltage at bus number 1 is V1. So better to write it here J 0.1 plus V2 and current injected at bus 2 is I2. So for first here first we are going to find this bus admittance matrix. So first we will write the KCL here. So from this figure number 2 we can write I1 is equal to V1 minus V2 divided by line impedance plus V1 into YC divided by 2. So here we can see that V1 is into 1 divided by Z plus YC 2 plus minus 1 divided by Z V2. So let us first find this 1 divided by Z plus YC divided by 2. So 1 divided by Z is equal to 1 divided by 0.03 plus J 0.04. So this will give you 12 minus J 16. So this Y12 we got. So here we can say that this is nothing but I1 is equal to Y11 V1 plus Y12 V2, and second element is 1 divided by mod Z plus sorry Z plus YC divided by 2. So first is 12 minus J16 plus J 0.1, 12 minus J 15.9. Therefore we can say that Y11 is, and this is symmetric matrix, so we can also this is like look symmetric from both sides, so it will be both diagonal elements are same. So y11 is equal to y22, that will become as 12 minus j 15.9. And since this admittance matrix is a symmetric matrix, so y12 is equal to y21, that will be minus 1 divided by z, so minus 12 plus j16. Therefore we are having with this relation, and this is bus admittance matrix for this two bus system. Bus admittance matrix for the two bus system by bus, or you can say it as y bus, right? Now let us see the if one quantities are known, then how we can find the other quantity. So let us first assume this voltage at bus, both buses are given. At the first bus, and it is given by 1.0 at the angle of 0 degree, and second voltage at bus 2 is given as 0.8 minus j 0.2. If you write it in phasor form, then this will be coming as 0.8 825 at the angle of minus 14.04 degree. So since we know that I is equal to YV, then we have to just put all these values and we can find the current injection at the bus 1 and 2 respectively. So here Y bus admission matrix is given by this and V is given by this, so we can get the bus injected at both the buses. At the bus 1 we will get 5.6 minus J 0.7, and at bus 2 minus 5.58 plus J 0.88. Now we can find this power injected at bus 1 and bus 2 respectively by using this expression. S1 is equal to V1 plus I1 conjugate, and S2 is equal to V2 plus V2 into I2 conjugate. Sorry, I said earlier wrong. S1 is equal to V1 I1 conjugate and S2 is equal to V2 I2 conjugate. So respectively we'll get power injected at bus 1 as 5.6 plus J 0.7, and at bus 2 minus 4.64 plus J 0.41. These all values are in per unit, right? So here we can see that we are getting minus of real power value, because at this bus power is not injected, power is being demanded at this that bus. So this is coming as negative of active power. Similarly, we can solve for the bus voltages if we are given with the current injected at the respective buses. So here we are given with the current injected at bus 1 and bus 2 as 5.0 and minus 4.8 respectively. So you can find the bus voltages by using this expression Y inverse, that is also as, and this is also, if you take this inverse, then it is bus impedance matrix Z bus. So the bus impedance matrix on being multiplied with the current injected matrix, so you will get the voltage at different buses. Now we can find the similar to previous slide, we can find the power injected at both the buses S1 and S2 by using this expression. S1 is equal to V1 I1 conjugate and S2 is equal to V2 I2 conjugate. Right, so in for the first bus, for the bus 1 we will get the real power injected is equal to 0.37, and for the bus 2 real power injected as 0.35. Since we are getting the this this voltages like very approximate to each other, so that's why we are getting the powers at both the buses approximately closing to each other. Now coming to this power flow analysis. So when we analyze our power system, we know neither the complex bus voltage nor the complex current injection, right? So here we have assumed the things, but in the real scenario we don't know the complex bus voltages nor the complex current injections. That is very important point for the power system engineers. Like we don't know the we neither know the complex bus voltages nor the complex current injections. Then what we are knowing about our power, about power system, about our system? So we are knowing this complex power being consumed by the load and the power being injected by generators plus their voltage magnitudes. So we have the known quantities are like the power demand from the load side and this power being injected by the generators with their voltage magnitudes. So these are the known quantities, but we don't know the complex bus voltage and the complex current injections. So therefore we cannot directly use these by bus equations, but rather we must use the power balance equations. So, so anyone can say that if we are knowing this bus admittance matrix, then we can directly find the current injected or bus voltages, but that is not the real case. Actually, these are the unknown quantities. Complex bus voltages and complex current injection are both are unknown quantities. We don't know. Rather than these values, we know the powers, like complex power being consumed by the load, that is the load demand power, and this generator, whatever the generator is the power being injected by these generators and their voltage units. That things we can know. So, but we are don't not doing this complex bus voltage and complex current injections at different buses. So therefore, we have must use the power balance equation so that we can find the different magnitudes in the power system at different buses in the power system. Now, how we can find this power balance equation? So again, we will use the KCL. So from KCL, we know at each bus I in a bus system, the current injection II must be equal to current that flows into the network. That I is equal to that the current being generated and this current demand IDI. So we can write is equal to K is equal to 1 summation of K is equal to 1 to N IIK. This we can write from the KCL. There are different lines connected to each buses, so that's why we have to write this in K form, the summation in the K form, so that we can we can take into account all the current injections being done at the buses. Now, since we know that I is equal to Y was V, so we can apply directly. We can apply here I is equal to Y was V. So how you can write IIK, current injected, at bus I with respect to the different buses, that is K, denoted by K. So we can write it as YIK, that is the admittance value of the line IK, current I the at which bus we are finding the current injection, and K with respect to which bus we are finding the current injections. YIK into VK, and VK is the voltage magnitude at the different buses. So we are going to just substitute this value here in this, and we will get this. We are going to substitute this value and we will get this equation. Now, if we are knowing this current injection at a specific bus I, then we can find the network power injection at that bus. So we will use SI is equal to VI I conjugate for that. So again, this II conjugate we can write from here. So II conjugate, how you can write? We have II conjugate, since current injection at a bus I is given as K is equal to 1 to N YIK VK. So current conjugate of that will be K is equal to 1 to N YIK conjugate VK conjugate. So we are substituting this value here. So we will get this one. So this is an equation with complex number. Sometimes we would like an equivalent set of real power equation. This can be derived by defining. So we are going to manipulate this term by using these following terms: yik is equal to gik plus jbik, and vi is, this is the conductance part, this is the conductance, and this is the susceptance element, and this is the admittance that we already know. So we are going to substitute these terms here in this one. Si is equal to Vi into sigma k is equal to 1 to n yi का conjugate Vk. Vi, that is magnitude of Vi is j theta I, Vi into angle theta I, that is phasor form, and this is in a, uh, and we also know that this Ej theta is equal to cos theta plus j sin theta. We are going to also use this expression also. So on substituting this all values, Si is equal to Pi plus Ji conjugate Pi plus J QI. So Vi into Yik conjugate Vk, we all know that. So put all this value Yik, we can write Yik, we know that Gik plus JVik. So therefore Yik conjugate is equal to Gik minus JBik, right? So this we get here, and Vk we have Vk we can write here. So Vk conjugate, put all these values here in this expression. So you will get this these values, and now we are going to resolve this into real and imaginary parts. So you will get Pi and Qi. So the net current active power injected at bus I is equal to Pgi minus Pdi, and this is the power balance. This is the equation that we are going to solve. And Qi, we are getting Qgi minus Qdi, that is the net reactive power injected at the bus I. Now this power flow, we assume that we know SI and the bus, we would like to solve for the voltages. The problem is that below equation has no closed form solution. We don't know the closed solution close we don't know the closed solution for this equation. Rather, we must have to pursue an iterative approach. That is the thing. So we are known with this power and the bus admittance matrix, and we now we want to solve for the bus voltages. But this solution has no closed form solution. Therefore, but this equation has no closed form solution. Therefore, we must go for an iterative approach. So there are different number of iterative methods that we can use, but here we will consider the Gauss and Newton methods, Gauss and Newton iteration methods. So first we are going to see the Gauss method. So here we need to rewrite our equation in an implicit form, that is x is equal to hx. To iterate, we first make an initial guess of x0, and then iteratively solve xv plus 1 xv until we find a fixed point x cap is equal to hx cap. We will see example how we are going to solve this. Uh, we can solve this type of equation by using the iteration method. How we can solve this type of nonlinear system with the help of Gauss iteration methods. So let us take the first example. Here we are having a nonlinear system, nonlinear equation, yeah, x minus root x minus 1 is equal to 0. So let us take xb plus 1 is equal to 1 plus x into 1 plus under root of xb. So first we are assuming this b is equal to 0 and arbitrarily guessed x0 is equal to 1. Now we are going to solve. So v is equal to 0, x v is equal to 1. So we will get it as 1. Now if we take at v is equal to 1, then what will be the value of x2? x2 is equal to 1 plus root of x1. So x1 is 1. So again we will get 2. Now x3 we will get 1 plus root of x2, and here, so here we will get 1 plus under root 2, that means 2.41421, and here x4 is 1 plus, so here you can write 1 plus 1, here it is 1 plus 41421, and it is 1 plus under root x3. Therefore similar, on putting all these values we can see that on putting the value of v is equal to 8 9, we are getting approximately same form. So we can say that what is the approximate equation, like if you put x is equal to 9, if you put xv is equal to 2.61798, then that will be coming as the approximate solution for this nonlinear type of system, nonlinear type of equation, because there is having a little gap between these two values, that is we are taking v is equal to 8 and v is equal to 9. So we will see that here we have to stop, either we have to go what should be the stopping criteria. So there is like we have to take some tolerance value. So what should be the minimum tolerance, what should be the that is we can accept. So if you see that upon going from 8 to 9, these three terms are equal, 617, and here also 617. If you take x is equal v is equal to 7 8 9, these three terms are coming after two decimal, it is a coming equal. So we can assume that we can take that xv is equal to 2.61798 as the approximate solution for this nonlinear system using the Gauss iteration method. Now, so as I said, what should the stopping criteria for the solving this type of nonlinear equation? So the here the key problem is to address is when to stop the iteration. With the Gauss iteration, we stop when this delta xv that I said earlier, the difference between two this xv at different v values. So here we can see that it should having some value epsilon, that is very minimal value. If it is coming less than that, then we can take it as the final solution. If it is more than that value, then we can go further and further. So this is the thing. Now if x is scalar, then this is clear, but suppose if this x is vector, then we need to generalize the absolute form by using a norm, and generally we having two common norms that we use in power system, that are Euclidean norm and infinity norm. So this first one is Euclidean norm, and this is Euclidean norm, and this is infinity norm. So, what we have understood that for solving this type of non system, we know how we are going to we have to apply the iteration method, but we don't know where we have to put the a stop, where we have to just end the iteration. So for that, we have some take some a small value epsilon that are going to decide the difference of that xv. So we have to calculate again this difference of xv, so that we can, if it is coming less than epsilon value, then we have to stop the iteration and we can take that this is the approximate solution for the nonlinear system using the Gauss iteration method. And now if this is a scalar, then it is okay. But if this is vector, then we need to generalize this absolute term by using the norms. And there are different norms that, like, we have Euclidean norm, infinity norm. So these are the expression for Euclidean norm and infinity norm. Now we see this Gauss power flow equation. So we first need to put the equation in the correct form. Then we want to know the voltage at different buses using the this power injection, using the power at different buses and the bus admittance matrix. So we know that S is equal to VI conjugate. So I conjugate we can write like this, and now we are taking the conjugate at both side. Take conjugate, taking conjugate at both side. So taking conjugate both side, we will SI conjugate VI conjugate II. So I we will get this expression, and we take it as VI to this and this left hand side. So we will get this expression, and now we will just bifurcate with with the bus at which we are finding the voltage. So we can take it as Yi Vi plus summation of k is equal to 1, k not equal to I to n Yik Vk. So where we are going to find the voltage, we take it at left hand side, and other things we take it at right hand side. So we will get the final expression for the voltage at different buses using the Gauss power flow method. Now let us take one example so that the things are clear. So here the question is that a 100 megawatt 50 MVA load is connected to a generator through a line with Z is equal to 0.002 plus J 0.06 per unit, and the line charging of 5 MVA are on each end 100 MVA base. Also there is a 25 MVA capacitor at bus 2. If the generator voltage 1.0 per unit, what is V2? So this is the generator voltage 1.0 at the angle of, and this line impedance is given as 0.02 plus J 0.06. S load is given as 1.0 plus, and this Y cap is given as J 0.25. All these values are in per unit. We have to find the voltage at bus 2. So first we are going to find the bus admittance matrix. So here the unknown is the complex bus voltage V2 to determine V2 we need to know Y was first. So the admittance of line is 0.02, 1 divided by 0.02 plus J 0.06, 5 minus J 15. And since shunt admittance is connected at the bus 2, so Y11, so we can directly write Y was, so what will be the Y11? 5 minus J15 and plus this shunt admittance. So directly write this one as 5 minus J 14.95 and minus 5 plus J 15. This one is minus 5 plus J 15, 5 minus J 14.70. So for susceptance for this B2T, how we have written, so B2 to have written as minus J15 plus J 0.05 plus J 0.25, as these are given in the problem. So now we apply this. The important part is that how we are going to apply this bus voltage equation. So we know that Vi is equal to 1 divided by Yii Si Vi conjugate minus k is equal to 1 k not equal to I to n Yik Vk. For this scenario, we have to find the bu bus at voltage at bus 2. So I is equal to 2 and n is equal to 2 because this is two bus system. So here we get V2 is equal to 1 divided by Y22 is to V2 conjugate minus K is equal to 1, K not equal to 2, N is equal to 2, I is equal to 2K VK. So we will get V2 as 1 divided by 2 is to conjugate divided by V2 conjugate minus Y21 V1. Therefore, 5 minus J 14.70 minus 1 plus J 0.5 V2 conjugate minus 5 plus J 15. Voltage at V1 is 1.0 at the angle of 0 degree. So here we have to assume we have to take the initial guess. So we can take the initial guess V2 is equal to 1.0, that is equal to voltage at bus 1. This is also known as flat start. This is known as flat start. If we assume the voltage at bus having voltage magnitude 1 and magnitude 0 degree. So it will be 1 point plus flat start is 0.01. If we take V value as 1, then 0.9671, J 0.0568, and 2 as 0.9624 minus 0.0553, 3 as 0.96 minus J 0.0, 0.9662, 0.0566. So we can see that upon going to value of V is equal to 3 to 4, there is very little difference change in the voltage value at bus 2. So these are equal. So we can take the voltage at bus 2 as V2 is equal to 0.9622 minus 0.0556. Therefore 0.9638 at the angle of minus 3.33 degree. So now if the bus voltage are known, then we can find the other things also in the system. Once the voltages once the voltages are known, all other values can be determined, such as the generator powers, such as the generator powers and line flows. So first we are finding the generator power SI conjugate. We know that VI V1 conjugate Y11 V1 plus Y12 V2. So we will get 1.03 minus J 0.239. Since base MVA is 100, so in actual units P1 is 102.3 megawatt, QS 23.9 MV.